In question number 121, we have N1 into N2 identical cells, and we have arranged these cells such that there are N1 cells joined in series to form one line, and then each of them are connected in parallel. And we need to find out the current in an external resistance capital R. And then there's a second question, we'll come to that. So first let's find out the current in the external resistance. What it is, the problem is saying, we have a cell of EMF E, internal resistance small r, then second cell, again small r internal resistance, and E is as its EMF, and third, fourth, fifth, up to N1 number of such cells are connected. So when these cells are connected in series, they're equivalent. We can replace this whole thing by one single cell, because these are in series, the cells are in series. So all their EMFs are connected, can be summed up, and we will have a total EMF of N1 times E. And then all these resistors are in series, so their equivalent resistance is N1 times of R. Now what we have done is, we have taken one of such pack, connected in parallel with the second pack, third pack, and up to N2 number of such pack. So this whole thing can be replaced with first N1E with N1R resistance, second cell of N1E resistance with N1R resistance, and similarly the third one, fourth, and up to N1. And then we are connecting an external resistor R, and we need to find out the current flowing through this resistor. So let us say from this cell a current I1 flows. Now all these are symmetrical. They have exactly same voltage, same internal resistance, and then in parallel. So if there is an I1 current flowing out of this battery, then an I1 current will flow out from this battery, and so on and so forth. On N2th of this circuit, an I1 current will flow from this circuit. And now all these currents are adding up here. So how many of them are? If one cell, if there are one cell, it was I1, or two cells will be 2I1, three cells 3I1, and two such cells, we will have N2 times of I1 current would be flowing through this. And this is the current. We need to find out N2 into I1 value, the current flowing through this resistance. The current flowing through this circuit is I1. What we need to do is, we need to apply the Kirchhoff voltage law in this particular loop. In this particular loop, we have a voltage of N1E right here, and that voltage supplies current to this resistor. The drop across this resistor will be I into R, I1 into N1R, I1 into N1R. Now, the drop across this resistor will be I, which is N2 into I1, N2 into I1 multiplied by capital R. Now we need to solve this equation to for N2 I1. We don't want to solve for I1 I2, because we need to find out the current flowing through R. So what we do? N2 I1 is right here. We need to get an N2 I1 here in this equation. So we multiply this whole equation by N2. So this becomes N2 I1 that we need to find out, multiplied by N2R here. And this becomes N2 I1 multiplied by the leftover N1R is equal to, if you multiply this one by N2, becomes N2 N1E. So we take N2 I1 common here. The leftover is N2R plus N1R. And we take it to the right hand side, which becomes N2 N1E divided by N2R plus N1R. And that is the current in the resistance. Now the second part is very interesting, and I hope you will like it the way I have solved it in this one. There are a couple of other methods also to solve this, but what we need to do is maximize the current, this current. Now there is one key thing into this. We have N1 into N2 batteries. For example, let's say if I have 50 batteries, then, or maybe let's choose another number, 60 batteries. We could choose 6 batteries like this and make 10 rows of this, or we could choose 5 batteries here and make 15 such rows to make 60 batteries. The question is, what arrangement of N1 and N2 in terms of capital R and R gives the maximum current in capital R? The first thing that you need to keep in mind that N1 into N2 is a constant K. We are given 60 battery. If we are doing this thing, then you need to keep another thing into mind, that N1 plus N2 is not the right thing. So N1 into N2 is constant, and then we have written is N1 into N2 is equal to K, and we need to keep in mind this is not the right constant. We are not given N1 plus N2 is equal to constant. We are given N1 into N2 is equal to constant, because we take N1 number of batteries in one row multiplied by N2 number of rows, and that is the constant K. We need to maximize this equation, so we write it I as a function of N1, and N1 into N2 is K, and we write it only in terms of N1, and we see what value of N1 maximizes. So N2 is equal to K upon N1, that's what we have written, K upon N1 multiplied by R plus N1R plus N1R. So this is as N1 varies in terms of K, R and R, then this current varies, goes to a minima and maxima. So Fn1 is max when this quantity in the denominator is minimum. So we call this quantity Gn1 is equal to K upon N1 into capital R plus N1 into R. Now we differentiate this one with respect to N1, and then we get minus K upon N1 square, Nx to the power of N minus 1. Minus 1 is 2. And n to the power minus 1, that's why we have a minus sign. And you differentiate with respect to N1, you get 1 into R. And for the G to be maxima or minima, this quantity has to be 0. Now you have the condition Kr divided by N1 square is equal to R. Instead of K, we write N1 N2 into capital R is equal to R. N1 and this square goes off. We have N2 capital R is equal to N1 into R. And under this condition, I will leave it to you verify that at this point d2g by dn1 is negative or something, and then or positive or whatever the condition applies for minima, and then at this point this current I will have the maximum value. You could also possibly solve it using another trigonometrical algebraic function, but there are other places where you can find that solution. Thank you.